So pay attention and pay attention to this. So you have the z-axis. As you can see in the diagram, pay attention please, pay attention. So let's just do this and go. You can see in the diagram that the z-axis is extended backwards. So I'm doing the same thing here. I'm just using dotted lines, but still the same idea. The label should appear only on one side, which is your positive side, okay? So you can already follow the extension at that end. So for this AB, you can see that, listen now, the projections on AB are two. The first one is parallel to the y-axis, and the second one is parallel to the z-axis. So we are reproducing the same thing here. That means AB, of course, this is our point A, and this is our point B. That means AB lies in the YZ plane, and the projection on this is going to be parallel to this now. So we have this parallel to the y-axis, just down, and the other one is parallel to the z-axis. So extend this parallel to this, we're going to have something like this. Is it clear? And for this, you have this angle to be 45 degrees. Does it make sense? Yes. Now, the force is our focus here. So let's deal with that force. We know the force is going to be directed from B to the given point C in the diagram. So we go from this point B to the point C in the diagram. We have something like this. So this is the point C. And for this point, how you know the direction is the fact that you have been given a projection also from here to the point C. So we are also told that the angle this makes with this is 8 degrees, and the angle this makes here is 30 degrees. Then you have 45 degree angle here. So our force is the tension in the cable, which is acting at point B. So if it is acting at point B, it should be directed away from point B. All together? So that means the force we are interested in will be along the line BC. So we say that the tail of that force will be here, and its tip will be here. Is it making sense? So this is the force F we are really interested in, and its magnitude is 6 pounds. Is it clear? Yeah. So I told you that for you to get the projections, just follow what it is from the two-dimensional case. If you have a two-dimensional force, so look at this illustration now. This x-axis and this is y-axis. And you have a force directed this way, for instance. If you want to get its x component and y component, you will first, from its base, that is from the tail of the force, project or extend a line that is parallel to the x-axis. You will have something like this. Extend a line parallel to the y-axis. You will have something like this. I want to get that, please. Respond now, respond.
Yes. Who will display your video?
So we have a line parallel to this. And from here, if I want to get the x component, I will project from the tip. And then I will go parallel to the y-axis. If I want to get the x component, I'll project down and get this component. If I want to get the y component, I'll project parallel to the x-axis. So I'm going to have something like this. And this will give me the y components. Does it make sense? Yeah. So we will do the same thing here in 3D. The limitation is that we want to write something that is three-dimensional on a two-dimensional surface. And the only way out is to always ask yourself, what axis is this line parallel to? What axis is that line parallel to? Once you are able to identify that, then you can identify what component or what axis is this component belonging to. Are we together, please? So the first thing here is to identify the force. We have done that. We know the force is from B to C. That means its tail is at the point B. And just like this force I have used for illustration, we should first extend a line out together Okay, parallel to our axis of interest. But that has been done for us already. They gave us this line, which is parallel to the y-axis, and another line perpendicular to the y-axis. So this thing here is perpendicular to this axis. That means this axis here is in the xz plane. Does that make sense? Yeah. That axis, this axis lies in the xz plane. So the first thing we identified here is the y component of the force. The reason for this resolution is the fact that every force can only be resolved into two components. Any force that you can imagine, you can only resolve it into two perpendicular components. And those two components will be in the same plane with the force. So the first thing is we have identified the plane of the force. Once we have the plane of the force, then the components will be in the plane of the force. So this is our force here. The plane of the force is already identified by this projection and this projection. Just like we have this here, this projection, this projection. By the time you close up the other gap, you are going to form the plane, and you're going to see that plane of the force very clearly. So, for this force, I can extend this projection so that it is parallel to this one. Just like I have this here, parallel to this. I can extend the other one too, just like I have this parallel to this. So this is the tip of the force. I can extend projections from the tip. So if I complete the base, now I have to go parallel to this. So that's going to be something like this. Okay? And from the tip, I'll go parallel to this also. That means it has to be parallel to this one. And then that gives me this. So that means that this line, this line, this line, this line forms the plane of the force. All of those are in the plane of the force. And with that, you can now resolve the force into vertical components and horizontal components. Or say, you can resolve the force into two perpendicular components. So the first component will be, when you project this to this side, you get the first component where it intercepts this. Just like for us to get the component, x component here. You project from this down here, where it intercepts this is where you have the tip of the components. And if you want to get a component to the y-axis, you project to this side. Where you have this is the tip of the component here. So we are doing the same thing. If you project from the tip to this side, you will have the tip of the y component. That's why we call this the Fy. Does that make sense?
Yeah.
Then, when you project this one up here, you are going to have the components that is perpendicular to this one. Is it making sense? That component can be called Fxz because it lies in the xz plane. How do I know it is in the xz plane? Because it is perpendicular to the y-axis. Is this very clear? Yeah. So, we have successfully resolved the force into two components along or in its plane. So the next thing to do is the other component that is not along any of the axes. We will now resolve it in its own plane as well. Does that make sense? That means we identify the plane where this is. It is in the xz plane. So we now have to resolve it inside the xz plane. Altogether, like I said, a force can only have two components. So I've picked the original force I was given. I've resolved it into y component and xz component. The next thing to do is now that xz component, I'll further resolve it into x component and z component. Why? Because it is not along any of the x, y, z axis that I'm interested in yet. Is it making sense? Is this making sense? Yes. Okay, so for us to do that, I said, because we have this angle here, it is better to indicate this component right here. It does not make any difference. It only simplifies our work because we have this angle indicated here and we can easily relate with it because our z-axis is here, our x-axis is here. Is it very clear? Yeah. So why can I put it here instead? It is just like this component I have here, this y component. I could have indicated it here. If I indicated it here, I have not done anything wrong. It is still the same force as what I had here. We say that two vectors are the same if they have the same magnitude and same direction. So whether I indicated the force here or here, they still have the same magnitude. This length is the same as this length. They still have the same direction because this is upward, this is upward. Is it very clear? So this fxz, I would rather have it here so that it is easy for me to resolve it into x components and z components. Is that very clear? So I will say that this is my fxz. So I'll put the arrow for that right here. So I know this is fxz, the component in the sz plane. So these components, don't forget this is the line for that component. Okay. Now that component is now our business. We have to resolve it into x direction and z direction. Again, we follow the same process as this. The first is the base of that force. From the base of the force, extend lines parallel to the axis of interest. What are the axes of interest now? X-axis and z-axis. So from the base of this force, I will extend lines parallel to the x-axis and parallel to the z-axis. So the first thing is what? The base of the force is here. So I will extend the line parallel to the x-axis. This is the x-axis. So extending the line parallel to the x-axis, I'm going to have something like this. Is that clear? Extending the line parallel to the z-axis. I mean, that is already provided in the diagram. So this is the line parallel to the z-axis. This is the line parallel to the y-axis. Sorry, x-axis. So what's the next thing? After doing that, you go to the tip of the force, Abi. So extend another line parallel to the y-axis and see where it intersects the x-axis. That will give you the x component. Extend the line parallel to the x-axis, see where it intersects the y-axis. It will give you the y component. So we do the same thing here. To get the x component, I will extend the line parallel to what? The z-axis. Wherever it intersects my x-axis will be where I have the tip of the x component. Does it make sense? Yeah. So I have this tip here. I will extend parallel to the z-axis. Don't forget this is our z-axis. So extend it parallel to the z-axis. Let me write this inside. So that's going to be this. Is that clear? Yeah. So here is where I have the tip of the x component. That will be my fx. Is it clear? Yeah. So what's the next thing? Extend from the tip again, parallel to what? The x-axis. And wherever it intersects the extension along the z-axis is where I will have the tip of my z component. So I will do the same thing. This is our parallel to the line parallel to the x-axis. So I will do the same thing here. I'm going to have something like this. Is it clear? So where I have this is the tip of my z components. Is that clear? Is that clear? Okay. So from all of this, we have been able to establish something. Now we have not found the magnitudes, but we have been able to establish something, which is the fact of which of the components will be positive or negative. So can you tell which of the components will be positive? So look at fx. Let's start with fx. Look at fx. Is it going to be positive? Yes. You go from this, it is moving towards the sign. I mean the label, sorry. So if it is towards the label, it is positive. Altogether, so we know that our fx, okay, is positive. What else? Fy negative because it's pointing down. Altogether. So for the fact that it is pointing down, what would you say?
It's negative.
Because it is pointing down, what would you say about that? It's negative. So Fy is negative. Sorry?
Fz is negative too.
What of Fz? Negative. Because it's away. Altogether from the label. So we identify all of those. Fz is negative. So now we are sure of what the directions will be. Now the next thing is what will be the magnitude of each of these forces altogether. So let's bother about that. And look at the information supplied in the question. Look at this angle 80 degrees. It tells you the angle that the given force makes with the horizontal plane. Is it making sense? Is this clear? This angle 8 degrees tells you the angle that this force makes with the horizontal plane. How do I know it's the horizontal plane? because I know this line is in the XZ plane. Is that very clear? That means this 8 degree here, if you like, is going to be the same as this 8 degrees right here. Is it clear?
Yeah.
So if you want to resolve this force, okay, this force F, its components here will be F cos 8 degrees. Is that making sense? And its component to this side will be F sine 8 degrees. Is it very clear? So let me write that out. This is what I'm talking about. The fact that F x z will be equal to F cos 8 degrees. Why is it cos? The side to which it makes the angle. When you are getting the component to that side, it will carry cosine of that angle. Does it make sense? And when you are getting the component perpendicular to that, it will carry the sine of that angle. Is it very clear? So it makes this angle with the horizontal component, which we call fxz. So the fxz component will be F cos 8 degrees. Does that make sense? So it means then that the other component, which is perpendicular to that, which is our Fy, will be equal to what? F sine 8 degrees. Does it make sense?
Yeah.
So what's the next thing? It was this Fxz that we then resolve into X direction and Z direction. So you can see our Fxz is making an angle of 30 degrees with the Z direction. That means our Fz will be Fxz cos 30 degrees. Are we together?
Yeah.
So we can write that out. Our Fz will be Fxz cos 30 degrees. Is it clear?
Yeah.
So what will be our Fx? Oh yeah, now speak. What is our Fx? Fxz sine 30 degrees. So this is Fxz sine 30 degrees. Is that very clear?
Yeah.
Is it clear? So we can now write out our force. So what do you think the force is going to be? Our force F. Now I want to write it in Cartesian vector form directly. So I have to take note of the signs altogether and also the magnitude. So I'm writing everything out directly. So our Fx comes first. This is Fxz sine 30. What is Fxz? Fxz is F cos 8 degrees. So the x component will be what? It is positive, Abby?
Yeah.
So that will be plus F. So what is F from the question? 6 pounds, Abby?
Yeah.
So I can just put that directly. This is 6 multiplied by cos 8 degrees. Then multiply by what? Sine 30 degrees. That will be I. Is that making sense? Then the next one is what? Fy. It is F sine 8 degrees. What is its sign? Negative. So that will be minus, what is F again? 6 multiplied by sine 8 degrees. Is it clear? And that will be J. And then the Z component, Fxz cos 30 degrees. What is Fxz? F cos 8 degrees.
Negative.
Yeah, that's negative. That will be 6 into cos 8 degrees. Then multiply by, I'll say 6 cos 8 degrees. 6 cos 8 degrees multiplied by cos 30 degrees.
Okay.
And that will be K. Is it making sense?
Yeah.
So with this, we have our force in vector form. And that is that about that. So we now have our R altogether from what we have done before. And we now have our F as well. So from this, we can get the moment of the force in vector form about the point A. So again, our moment is simply equal to R plus F. You can write that out in vector form. I, J, K. R comes first. We found R the other time to be this 6 feet, Abby? Cos 45 degrees negative, Abby? For the Z component. It was minus 6 cos 45 degrees. So you can put that right there. And then the Y component was plus, Abby? So it was 6 sine 45 degrees. And this will be 0. Is it making sense? So you can now put this one there. So just give me this in number form, or just write it there directly, anyhow you want to do it. 6 cos 8 degrees multiplied by sine 30. Sine 30 is 1 over 2, so I can write this as 3 cos 8 degrees. Then I have this as minus 6 sine 8 degrees. And this is going to be cos 30 is root 3 over 2, so I can write this as 3 root 3 minus 3 root 3 cos 8 degrees. Do you understand that? So you can deal with this with your calculator. It should give you your results directly. So want your calculator and you are good to go. Alright, ladies and gentlemen, I think with these few points of mine, I've been able to convince you and not to confuse you that ME205 is very simple. Alright, thank you for coming. We'll continue from here.